You've just investigated the alternating harmonic series. Let me go ahead and go over to the Desmos graph here. I've added several more terms to the graph. And what this is suggesting, as you can see, is that the partial sums here in red are leveling off to some number that's approximately 0.69. So in fact, this series does converge, and we'll see a lot more of this series coming up. All right, whoops, I apologize about that. Okay, so we have a convergent sum here. We'll talk a little bit more about how we can see that sum converges just in a second here, but I just want to highlight the difference between the harmonic series that we talked about a couple of classes ago and this series, the alternating harmonic series. So the only difference formulaically is this minus 1 to the k plus 1 term here that's adding minus signs every other term. And the positive parts here are identical. But in the case of the harmonic series without the minus signs, the series diverges, so it does not converge. Right, so we saw there the partial sums just kept increasing. Oops. For the harmonic series. On the other hand, for the alternating harmonic series, the terms, because they're being alternately added and subtracted, the partial sums, as you could see on the previous page, are seeming to level off. And so the insertion of the minus signs is making the partial sums increase and decrease every other time, and so then it's easier for them to bounce around a single limiting number. So let's talk a little bit more about this kind of series. It's that where the signs of the terms are alternating from positive to negative. It turns out for these kinds of series, there's a really nice characterization for when the series will converge. So the alternating series test is what I will just go ahead and highlight for you here, right? So the point is, if you have an alternating series, okay, I'm not sure what I'm doing here. Let me get rid of that. What I meant to do was to point out to you that the exponent here has gotten pushed up from my equation editor, and that's not, so it looks a little funny, but this is just a standard minus 1 to the k plus 1 power times AKs. And here the AKs are all greater than or equal to 0. And so they're positive. And then there's this minus 1 to the k plus 1 on the that's being multiplied there. So that's causing the signs to alternate. So it turns out that if we have such an alternating series, then if it's the case that the jump sizes are strictly decreasing, it's a little bit informal here, and they decrease toward 0. That's this, when I say jump sizes decrease towards 0, that's combining 1 and 2 here. So if those two things hold, then the series has to converge. So let's talk about why that is. It's also true that that if the jump sizes are decreasing and don't decrease towards zero, then the series doesn't converge. So let me remark, if the limit of the positive parts doesn't equal zero, well, this is just actually an extension of the divergence test, right? If the limit of the positive parts doesn't equal zero, then the limit of the overall terms isn't going to equal zero. So by the divergence theorem, the series doesn't converge. Okay, so so let's talk about why, if the jump sizes do decrease towards zero, the series must converge. I think the easiest way to see this is by looking at a picture. And so what we have been looking at in terms of visualizing series has been thinking about graphing the partial sums, right? So if we have 1, 2, 3, 4 here, then we plot S1, and then we have S2, and then S3 and S4 plotted here. So a plot like this. But I think actually the most clear picture for why the alternating series test works is by actually just plotting these heights just on the number line. So if we just have the number line here, and we start with S1, and let's do S1 for the harmonic series. Suppose S1 is 1, S2 is 1/2, right? Because it's 1 minus 1/2. Okay, and S3 is right here, so it's 1 minus 1/2 plus 1/3, and so on. So I'm going to go ahead and just plot what's happening in terms of these jumps. And so we're jumping back by 1/2, and then to get to the next term, we're jumping forward by 1/3 to get to S3, and then to get to S4, we're going to jump back by 1/4, and so on. So what you can see is that as we're jumping back and forth along these purple jumps here on the number line, where we land are these points, the partial sums. And you can see that those partial sums are honing in on they're continually zigzagging in towards a single limit. So let me just write that here. Partial sums zigzag. It just means they kind of bounce back and forth. So they zigzag towards a limit S. Okay, and how do we know that they have to go towards a limit? They zigzag towards some limit S because the jump sizes decrease to 0, or decrease toward 0, I guess I should say. Okay, so there is some limit s. Let me go ahead and pop that in here in another color. So here's my limit s. Right, and in the next jump here, we're going to have S5. This is 1/5, right? And then we could zoom in even further. Okay, I think I'm at the limit of where this will zoom. But in my next jump, I'm jumping back by 1/6, and here's S6. So what you're seeing then is that the zigzags, the amount that we're jumping by, is decreasing. And so eventually, if I'm looking at this picture, eventually the partial sums are clustering at S. Okay, so that's kind of a heuristic graphical picture of why the series converges. And I'd like to just point out that that really heavily relies on these jump sizes going to 0. Because if the jump sizes don't go to 0, suppose the jump sizes are always, like approximately a half, right? I can just start zigzagging back and forth and back and forth and back and forth, and I'm never actually getting close to any single point because I'm always hopping back and forth over it. So I just want to point out that that's a pretty strong requirement here. In fact, as I remarked up here, if the limit of those jump sizes is not 0, then already the divergence theorem says that the series won't converge. Okay, so let's talk a little bit about the next clause here. So your book actually splits those into 2 separate theorems, but I think the process of analyzing this graphically, you really see the second result at the same time. So the first part, maybe before we actually move on here, I'll just say this is something you can check very quickly, right? You can just see what are the AKs doing. Are they decreasing at every stage? And is the limit of the step sizes going down towards 0? And if that's the case, then you absolutely already know that the series converges. By the way, because convergence only depends on the tail, as long as your series is eventually alternating and the limit of the terms is 0, then you still have series convergence. All right, so now let's talk about an observation that we could have made already at this stage here. So I'd like you to notice here, this limit S, every time that we take a jump, so every time we add a new term, we hop over that limit S. Okay, so why is that? Because once I go from S1 to S2, I can never, ever come back because my next jump cannot be bigger than than 1/2, right? I can never get back to anything bigger than S1. And once I leave S2, right, and jump over here to S3, I can never come back to anything less than S2 because my next jump cannot be more than 1/3. And so each time that I take a jump, I know that the limit cannot be outside of, so let me say that another way. The limit cannot be outside of any 2 consecutive terms. In other words, the limit S lies between any 2 consecutive partial sums. Okay, so let's think about that then. So we know that the limit has to be in between 2 partial sums. Let me go ahead and just draw a third picture for you here. So if I have, let's just go ahead and put Sn here and Sn plus 1 here, right? And so what did I add to get to Sn plus 1? I added An plus 1 to get from here to here. And I know that I've jumped over so the limit has to be somewhere in between Sn and Sn plus 1. So another way to say that is that this distance here, right, that is the distance from S to Sn, has to be less than or equal to this overall distance between Sn and Sn plus 1. And this distance is equal to An plus 1. So the second part of this is just coming from exactly that observation that we made in the process of thinking about why the alternating series test works. What this allows us to do is say that the difference from any partial sum to the limit is at most the size of the next term in the series. And so that gives us a way of saying how close we are to the true limit from any particular partial sum. And so we'll do an example of that next. So I guess before we do that example, let me just comment the alternating series test. The alternating harmonic series that we had up above fits this alternating series test because first of all the terms are alternating, and second of all the terms decrease. So if we were going to check that the alternating series test applies here, we would note that 1 is greater than or equal to 1/2, which is greater than or equal to 1/3, which is greater than or equal to ... And here, again, what I'm stripping out are just the positive parts of the series and checking whether those are all positive. And then the other thing I would need to check is that, so here's checking part 1, and then checking part 2, we would check that the limit as k goes to, oops, sorry, this is getting a little crowded here. I'm going to go ahead and move this up here. We would need to check that the limit as k goes to infinity of 1 over k is equal to 0. And that, of course, is true. So since both of these things are true and we have an alternating series, then this alternating series test that we've just argued here graphically tells us that this series does in fact converge as our intuition from the graph told us. So, okay, so now moving on to the second statement that the sum of the series lies between any two consecutive partial sums, and this inequality right here. Let's go ahead and do activity 8.4.4 to show how this can be useful. So the idea here is to determine the number of terms that it would take to approximate the sum of the convergent alternating series to within 0.00001, right? And so what we want to find n so that S minus Sn is less than or equal to 0.00001, right? But we know that S minus Sn, so by, let me go ahead and just call this star. So by star, and I think your book calls this, what are they calling it? They call this the alternating series estimation theorem. Let me go ahead and just write that here. This is the alternating series estimation theorem. Okay, so by star, then what we know is that S minus Sn is always less than or equal to An plus 1. Okay, so what is An plus 1? Well, it's 1 over, and instead of a k here, I'm going to put n plus 1 to the fourth. Notice I'm not putting the minus 1 in here at all because the a is just the positive part of the series. So what we want is for this S minus Sn to be less than or equal to 0.00001. So let's go ahead and set this equal. We need 1 over n plus 1 to the fourth to be less than or equal to 0.00001. So let's go ahead and, all right, so let's see, 1, 2, 3, 4, 5. So this is 10 to the minus 5. And so if we solve this, we end up with n plus 1 to the fourth is greater than or equal to 10 to the fifth, right? And then we can take the fourth root of 10 to the fifth. Okay, and so taking the fourth root, we can just divide by 4 here. It has to be less than or equal to n plus 1. So n has to be greater than or equal to 10 to the 5/4 minus 1. And so here you could actually plug this into a calculator. If you just want to find some number of terms, I would just, 5/4 is less than 2, so you could certainly say n bigger than 99 would work, but certainly something much less would work as well if you were going to be calculating these by hand. Okay, so we're going to go ahead and I'm going to pause here. What we're going to continue with is a discussion of absolute and conditional convergence. And so to do this, there's a nice introductory activity in your book that investigates these ideas. What these ideas talk about here are more general series than just alternating series, because certainly for alternating series we have a really good characterization of when a series converges. But the discussion coming up in your book that activity 8.4.5 deals with talk about series more generally, so the signs don't have to strictly go back and forth. But the series do not necessarily have all positive terms. So what I'd like for you to do is go ahead and we'll stop this portion of the video right now, and I'd like to give you time to work through 8.4.5, and then we'll tie it all together and discuss the ideas of absolute and conditional convergence when we return.